Okay, so last talk of the day and last talk of the winter school. So Andreas Hülsing from Eindhoven University will cover hash-based signature.
Okay, thank you for the introduction. So let's start immediately with some motivation. You already heard this 2 days about lattices, MQ, and coding. And so we can build signatures in theory from all of these 3 fields. However, the problem is some of them have signatures and or key sizes which are incredibly large. So sometimes this goes up into megabytes. That's something you do not really want in practice. So as Tanya said in her talk this morning, like if you go to the CFRG and tell them like, yeah, I've got 1 megabyte keys, then they say, yeah, we don't care, go somewhere else. For others, the runtimes are really an issue. So if you build up an SSL connection, you do not want to wait a minute until the signatures are verified or actually generated during the handshake. And the most important issue, I think, is secure parameter selection. So for many schemes, we do not yet know how to select secure parameters. If you look at lattices, for example, we know a lot about asymptotic behavior of the problems. But really selecting parameters where we know, like, OK, for the next 40 years, these parameters are secure, that's still an open problem and also a moving target. So you sometimes have schemes where people say, OK, these parameters are 100 bits secure, and the next year they say, well, perhaps it's only 80 bits. That's something you can do in research and practice. You cannot do this. OK, so there's an alternative, which is, I would say, to some extent, a lot simpler than these previous candidates. It has the disadvantage that you really can only build signatures. So that's the only post-quantum area where you don't have encryption or something like this. And, well, these schemes are post-quantum. That's why I'm here. They only require a secure hash function. I will comment on this in a second. The security is well understood. I will also talk about this in a second. And the schemes are comparatively fast. So especially the stateful schemes are faster than RSA on some hardware, for example. OK, so they only require a secure hash function. Why is this a difference to other schemes? So if you look at how signature schemes in general are built, then we start from some intractability assumptions. So this can be RSA, the Diffie-Hellman problem, the shortest vector problem, the MQ problem, whatever. And then we combine it with the cryptographic hash function. And that's something all these schemes need at least to get message compression done. So if we want to handle arbitrary message sizes, then we need a secure hash function anyway. And we add an additional assumption that has to be hard. So both of these have to be secure to get a secure signature scheme. If one of these 2 assumptions fails, so like this, the assumption that the hash function is secure or the assumption that a certain problem is hard, then our scheme becomes insecure. And the nice thing about hash-based signatures is we get rid of this intractability assumption. So we do not need a second additional assumption besides the security of the hash function. OK, so let's talk a bit about what are hash function families. So in general, I would talk about families. In practice, you've got something like the SHA-2 family, for example, which actually consists of a single function. So people in theory like to consider this in a way that, well, the IV, so the initialization vector of the hash function, is a random string which selects a random element from this function family of SHA-2. And so in this sense, we've got a family of functions, each of them called HK with some key space. So the key here might be seen as some description. For example, it could be the initialization vector. Then these functions map bit strings. So I'm restricting here to bit strings because that's what we're using in practice. The extension to general input spaces is kind of straightforward. So they've got an input space, m of n, so n is the main security parameter here, and they map mn bit strings to n bit strings. So m is a function of n, and we normally consider m of n to be bigger than n and normally polynomial bounded. So often m is something like 2 to the 64. And we want these functions to be efficient. So in practice, this means really efficient. So like in a few cycles, we can compress short messages. In theory, we will simply assume these are evaluatable in polynomial time. Okay, so that's the functional description. Now we want some security properties of these hash functions. The first very basic one, and that's like the smallest possible assumption we can make in complexity-based cryptography, is OneWayness. So if we got such a function family, then OneWayness can be defined as a game where an adversary receives an input y, c, and a k. So k is a function description that describes a uniformly random function in this family. And yc is computed by sampling a random element from the domain and then evaluating the function. So this is a bit different. You could also define it simply sampling yc from the range, but then you're not guaranteed that yc actually has a pre-image. So that's why it's defined this way. And now the task of A is to find some x star such that x star, given this input to hk, evaluates to yc. So it's simply inverting the function. The next one is collision resistance. So you're given a random function from the family, and the attacker then is asked to find two inputs which collide under this family without being equal. So I think that's stuff most of you will already know. The third property is second preimage resistance. That's something like a pointed collision resistance where the attacker gets a random element from the domain and a description of a function and has to find a second element from the domain that collides with this value. Okay, now the first property that you might not be too familiar with, that's called undetectability. And I think it first appeared in a paper by Dode, Smart, and I don't remember the third author. And that's a distinguishability notion. And it roughly says an attacker cannot distinguish the output distribution of the function from the uniformly random distribution over the range. So the game works as follows. We sample a random element from the function family, and then we do one of two things. We sample a random bit, and if the bit is 1, then we sample a random element from the range and compute an output of the function using this input. In the second case, if the bit is 0, then we simply output a random element from the range. And the task of the adversary is to distinguish these two cases. So that's a bit like the pseudo-randomness property of a pseudo-random generator, just for compressing functions. Okay, the last property is pseudo-randomness. So a pseudo-random function family is a family that is indistinguishable for an attacker from a random function family. And this is defined in terms of the following game. So you've got an attacker that gets access to some black box that implements a function g. And the attacker can ask this black box for the evaluation of some function g on several points and will get like the evaluation of the function, and in the end has to output a bit b star. And now this bit b star should match the bit b, which is an input to g, and if the bit is 1, then g is actually sampled from this function family, so it's a random element from this function family. If it's 0, then G is simply a uniformly random function from a family of all functions with the same domain and range. Is this so far clear for everyone? Okay. So now I want to look at the generic security of these function families. What do I mean with generic security? So that's kind of a black box security notion. So the best that we can do without looking at the internal structure of the function family. So for hash functions, you can do this by analyzing the resistance or the security in terms of these properties for a random function family. And I will express it in terms of the number of queries that an attacker has to make to the function family to break a property. And the reason why this is important is for hash functions, we do not really, like the hash functions we use in practice do not rely on some hard problems, but they are constructed in an engineering-like way. And the requirement is that the hash functions meet these generic security bounds. So if a hash function allows for attacks that are more efficient than these generic attacks, then it's considered insecure. So we had this for SHA-1 now, for example, which in the beginning was not practically broken, but theoretically broken, meaning we had collision attacks with a complexity of 2 to the 64 at that point, which is not practical, but it's clearly below 2 to the 80, which would be the generic complexity for a collision attack. Okay, so just as an example, let's go through the generic security for one-way functions. So in the classical case, if an attacker does not make any query, then the best he can do is simply guess an input. So he makes a random guess, outputs this guess, and he will succeed with probability 1 over 2 to the n of hitting actually this target yc. The reason is if you think of the function as a random function, then you can think of it as for every input, it simply samples a random element from the output range. And so every element from the output range, if the range has size 2 to the n, appears with probability 1 over 2 to the n. Okay, if I do one query, then what I can do is I can make a guess. Then I can use my query to verify this guess. And if I didn't hit the image, then I output some new guess. And in total, I got a success probability of 2 over 2 to the n. And so if I have q queries, I can repeat this procedure q times. So I guess, then I check, then I guess, then I check. And if I didn't find a valid solution in the end, then I output a new guess. And in total, I will get a success probability of q plus 1 over 2 to the n. Okay, I think that's kind of straightforward. And so the query bound is 2 to the n. So I need 2 to the n queries, or order of 2 to the n queries, to actually get a constant a constant large enough success probability, so around 1/2. And actually, this algorithm also tells me like how I can achieve this attack complexity. So the quantum case is a bit more complex. We got a paper at PKC now where we analyzed this in detail. What we did is the reduction from quantum search for some random function. And the nice thing is that we know lower and upper bounds for quantum search. So by getting this reduction, we immediately get a lower bound on the query complexity. In this case, it turns out what we guessed before but didn't verify before, it's 2 to the n over 2. And for the upper bound, you can simply apply some variant of Grover that also works in the average case and analyze the success probability. And then you get the upper bound. Currently, the proof that we did requires 2 to the m to be clearly bigger than 2 to the n. So we need something like m equals 2n, then we are fine. But if they are equal, then this reduction doesn't work anymore. So it's a bit annoying. So these properties are around for some time, and we somehow know that we can apply Grover, but no one really looked into if these also hold for random function families. Okay, and so we can do this for all the properties that I showed before, and then we get, for OneWayness, second pre-image resistance, undetectability, and pseudo-randomness. We always get a complexity of 2 to the n in the classical case and 2 to the n over 2 in the quantum case. So these are just conjectured, so there we don't have a formal proof yet. For collision resistance, we've got clearly stronger attacks. So in the classical case, we've got the birthday attacks, which give us 2 to the n over 2. And in the quantum case, we actually do not gain as much as for the other properties and only improve this to 2 to the n over 3. And if you ask Dan that looked into the storage consumption of this algorithm, he actually claims that this is not really better than a specially built classical machine for the same purpose. Okay, so there is actually some theoretical background why collision resistance is that much easier to attack. So the point is, if we start from a one-way function, then we can build pseudo-random function families from this, and we can also build second pre-image resistant function families from this. And we can get pseudo-random generators, which are undetectable. But collision resistance is clearly a stronger property, so we cannot go from second pre-image resistance to collision resistance. And in a complexity theoretic view, this lower part belongs to something called mini-crypt by Impaglazio, and collision resistance already belongs to cryptomania, which contains stuff like public key encryption, key exchange, and so on. So these are things that you cannot build from a one-way function without any additional assumption. Okay. In practice, this also has some influence. So on the one hand, of course, because of the attack complexity, if we look at the classical case, if we require a function to be second pre-image resistant and we want b bits of security, then we have to choose the output size just of length b. If we want collision resistance, then we have to select the output size of length 2b. So we double the output length, and in hash-based signatures, signatures and keys are just a collection of hash values. So this is simply a factor of 2 that you lose in terms of the size. But there's also a different point of view in the practical case. So if you look at collision attacks or attacks on hash functions in general, then we had collision attacks on MD5, which was used as a standard for a long time in 2004. In 2005, we had the first theoretical collisions for SHA-1. In 2008, we had the first practical collisions for MD5, where people really forged a CA certificate. And we do not have any MD5 or SHA-1 second pre-image or pre-image attacks so far. And as far as I know, we are still far off from this. So if you want to be provocative, you could say, like the schemes that we're constructing, you could actually even instantiate with MD5 and they would still be secure. I would never do this, but I don't think that anyone yet could break it. And actually, there just appeared a paper, or will appear now at Eurocrypt, where they got the first practical free start collisions for SHA-1. So this is really in progress, but for the lower properties, they do not have a lot of ideas how to do this yet. Okay, so coming to hash-based signatures. The very basic construction, okay, so hash-based signatures are centered around so-called one-time signatures. So one-time signatures are signature schemes where I can use a key pair just to sign a single message. So when I use them to sign one message, I have to generate a new key pair. Okay, while this is not practical, I will explain how to extend this later, but first look at such a scheme. So the first scheme was a scheme developed by Lampert, and some papers call it Lampert-Diffie OTS, so I stick to this name. And it considers an m-bit message with bits b1 to bm. It uses a one-way function h, which formally would be assumed to be sampled from some function family, and such a block denotes n bits. So the secret key consists of two m secret key blocks, which are simply uniformly random n-bit strings each. And they are ordered in pairs. So we got here a secret key 10, a secret key 11, then we would have secret key 20, secret key 21, and so on until secret key m0, secret key m1. The public key simply consists of the outputs of the hash function using these secret key elements as input. And our signature consists of a selection of secret key elements. And what you're doing is, from each of these secret key pairs, you select one depending on the corresponding bit of the message. So you use bit 1. If it's 0, then you use SK10 in the signature. If it's 1, then you use SK11 in the signature. And so on for each of these pairs. Now, if you verify the signature, then you simply apply the hash function to each of these signature values and compare the output to the corresponding part in the one-time public key. Anyone guess why this is a one-time signature? It's late, you're tired, okay. So if an attacker would be allowed to ask for two signatures of his choice, he could take any two complementary messages. So for example, the all 0 and the all 1 message, and would immediately learn the whole secret key. And thereby he would be able to sign any message of his choice. So that's the reason why I must only use such a key pair once. And then I need a new key pair. And just to give you an idea of how the security proofs for the stuff work, so I will briefly go over the existential unforgeability and the chosen message attacks proof for Lampert-Diffie. So existential unforgeability and the chosen message attacks in the one-time signature setting means you get an adversary that gets the public key as input, and then he gets access to some signing oracle, which is initialized with the corresponding secret key. And he might ask for the signature on one message of his choice, and then receives back this signature with the message. And then he has to come up with a new signature message pair such that sigma star is a valid signature for m star, and m star is different from m, so from the message that he asked a signature for. And if you go to the general signature case, then you can repeat this q times for some q. Okay? And now what I want to prove now is that if the hash function that we use in Lampert-Diffie is one way, then the signature scheme is one-time, existential unforgeable, until chosen message attacks. Okay, so we've got a reduction where we get such a one-way challenge pair. So we get the description of a hash function and an image under this hash function. And we are asked to find a pre-image for this value. And now what we do is we set the hash function used in the Lampert-Diffie scheme to be this hk, so described by this k. And then we generate, using the normal key generation algorithm, some Lampert-Diffie key pair. And then we select a random public key element by sampling a random I and a random bit B, and place our OneWayness challenge there. So this means I do not know the secret key element for this one, but for all the others, I know the secret key elements. Now I will start the adversary that can forge signatures for Lampert-Diffie. And the adversary will eventually query for the signature on one message of his choice. So let this message be B1 to BM, then I can simply answer this query if here I assume I was 2 and B is 0, then I can answer the query as long as the ith bit, so the second bit of the message is not 0. Because for this one I do not know the secret key element. So in this case, if I would be asked for a message which has the second bit 0, then I would have to return fail. However, in the other case, I can simply compute the signature using the normal sign algorithm and return the signature. Then at some point, the adversary will come up with a forgery. So let's call these B1 star to BM star. And now, if the ith bit is unequal to B, I return fail, because in this case I didn't learn anything new, because then I might have learned a second pre-image here, but actually I didn't ask for this. Otherwise, if the bit is B, then I output the signature element at this position, and this will be a pre-image for YC, because otherwise the signature would not be valid. Okay? So this shows I can turn any forger against the signature scheme into an attacker against the OneWayness of the hash function. Well, I cannot always do this, or my success probability gets a bit lower. So if I analyze this, then I abort in two cases. The first case is in the beginning when the adversary sends his query. If the ith bit is B, then I will abort. The probability for this is 1/2, because from the public key the adversary cannot learn at which position I exchanged the real public key value with my challenge value. So both are random outputs of the hash function. So with probability 1/2, he will use the other bit. And in the second case, when I get the forgery, I need that the bit in the ith position is actually B. So this is conditioned on that actually the bit of the query message at this position was unequal to B. Now, the attacker has to flip at least one bit in his forgery message, because otherwise the messages would be equal and this would not be a valid forgery. So with probability 1/m, actually, he will have flipped exactly this bit. And so in total, the reduction succeeds with a success probability times 1/2 times m, which is kind of tight. So we only have a small loss in the reduction. Okay. Now we know how to build a one-time signature scheme. How can we do many signatures? So we start with a one-time signature scheme, and then we generate many one-time key pairs. And then, so this actually would already be a many-time signature scheme. I mean, you would simply get a public key which consists of all these one-time public keys, and a secret key consists of all these one-time secret keys. Would work. However, in practice, the public key would be enormous. So that's where Merkel's idea comes into play, and why these schemes are often called Merkel signature schemes. So Merkel proposed to build a so-called Merkel tree, which is a binary hash tree, where you use the hash values of the one-time public keys as leaves, and then compute this binary hash tree, where you always concatenate the outputs of two child values and then hash it to obtain the parent node. And the root value of this tree becomes your new public key of the Merkel signature scheme. And the secret key consists of all the one-time key pairs. And actually, I didn't go into this in this slide set, but if you remember, the secret keys are simply random bit strings, and it's straightforward to use a small random seed and expand it into many pseudo-random bit strings. So thereby you can actually get a secret key size of n bits and then simply generate these one-time key pairs as needed. Okay, so as I said, we must not use these one-time key pairs more than once. So the easiest way to avoid this is to use them from left to right and simply store where you currently are. So if you do the second signature, then you put into the signature the index 2, and you use the second one-time key pair to sign a message, and then you put the one-time signature and the one-time public key into the tree signature. And in addition, you put these nodes here, which are called the authentication paths, into the tree signature. And these nodes are later used by a verifier to verify the authenticity of the public key. So verification works as follows. The verifier uses the one-time public key to verify the one-time signature on the message. And then, given the index and these authentication path nodes and the one-time public key, he can start to compute this path up to the root, and he will eventually obtain some alternative root value. And then he can compare this value to the public key value. If these two match, then the one-time public key was authentic. If there's a different one-time public key, then actually you would get a collision somewhere on the path. And that's something I will show again in the proof, and this will be the last reduction in this slide set. So I will prove that the Merkel signature scheme, as I described it in the last slide, is existential and forgeable under chosen message attacks if the one-time signature scheme is one-time EU CMA secure and H is a random element from a collision-resistant hash function family. And the proof works as follows. So this time we either will output a collision or forgery for the one-time signature scheme. And so we get a description of a function family K, a description of a function, and a one-time public key. And then we generate a key pair as before using keygen. And then we replace a random one-time public key by the one we were given and rebuild the tree using the hash function that we were given. And then we can answer all the signature queries that an adversary makes, because we know the secret key for all but this, this one key pair where we place this given public key OTS. But for that one, we got access to a one-time oracle where we can send one message and we'll get the signature back. So we can answer all of these, and then in the end, when the attacker comes up with a forgery, we will either extract a one-time signature forgery or a collision from this forgery. And this works as follows. So we look at the forgery and first compare the one-time public key in this forgery with the one-time public key we used at this position. If these two matched, then the attacker obviously forged the signature for the one-time signature. And this can be used if this happened exactly for the index where we place this target one-time signature scheme. In the second case, and that's the main point here, if these one-time public keys do not match, then this means that actually the attacker placed a new one-time public key into the tree. So he changed one of the leaves in the tree. And then the two authentication paths start with different values, but in the end up at the same root node, because otherwise the signature would not verify positively. And so by the pigeonhole principle, there must be some point where these two paths collide, latest at the root node. And this collision will be a collision for the hash function. Okay. Any questions so far? Yes?
Do you have any? When you initially set up the public key, the number of signatures you can generate is
Fixed.
fixed.
Yes.
Do you have any other methods to increase later? Do you have any?
You can speak and I repeat the question.
Do you have any way to increase the number of signatures we can generate later?
So the question is if there's a way to increase the number of signatures later, like after key generation. No, we don't. So at that point, you simply need a new key pair. So if we have a tree of height h, then you've got 2 to the h leaf nodes, so you can do 2 to the h signatures. We've got two messages, actually one way to deal with this. We got ways to build trees of height 2 to the 60, and you will never do 2 to the 60 signatures. So that's kind of virtually unlimited. Comes at the cost of slightly bigger signatures, but yeah, I've got numbers later in the slides. Okay, so I started with the Lampert-Diffie one-time signature scheme because that's kind of the easiest schoolbook-like example of a one-time signature scheme. However, it's also, I think, the least efficient one of the hash-based one-time signature schemes. And currently the most efficient one, especially for the use in hash-based signatures, is the so-called Winternitz one-time signature scheme. And I will develop how this was actually constructed. So if you remember Lampert-Diffie, then we had a bunch of random n-bit strings as secret key, the hashes as public key, and we selected from each of these pairs one element depending on the bits of the message. Now, if you look at how this is used in a Merkel signature scheme, then the verification works in two steps. So first, you verify the one-time signature using the one-time public key. And then, independently, you verify the authenticity of the one-time public key using the tree and the authentication path. But we can actually do better. And the first very straightforward trivial optimization is as follows. Instead of only outputting some secret key elements for a signature, we can output from each pair one secret key element and one public key element. So if, for example, the first bit is 0, we would output SK10 and PK11. And the other way around, if the bit is 1, then we would output SK11 and PK10. This might seem a bit stupid in the first moment because we're actually increasing the signature size without gaining anything. However, if you look at how this can be used in a Merkel signature scheme, then you will see the following. We can actually remove the one-time public key from the Merkel signature. And the reason is as follows. So the verification can be done now by computing the one-time public key from the one-time signature. So in this case, this simply means we apply the hash function to all the secret key elements in the signature. The positions are defined by the message. And then we verify the authenticity of this computed public key. Now, if the signature was invalid, this would mean that we compute a different one-time public key. And thereby, if we fall back to the proof, this would be a new leaf in the tree, which means we get a collision within the tree in the hash function. Okay? So in this case, we can skip this first verifying the signature with the one-time public key and then verifying the one-time public key, but we simply compute a one-time public key from the signature and then verify the authenticity of this one-time public key by using it to compute a new root node and then computing this, comparing this root node to the node we are given in the public key. Okay, now this was the first step. Now we can sort the stuff and simply kind of resort. So it's a bit ugly to have this two subscripts. So we can simply number the secret keys from 1 to 2m. And then the public keys have the same numbering. We still got 2m secret key and public keys values as before. And now if we encode the message as m concatenated with its bitwise negation, then we actually obtain the exactly same signature scheme as this trivial optimization that I presented before. If the signature consists of the secret key element, if the ith bit is 1, and the ith public key element if the ith bit is 0. So this is actually just a reordering of this one. So just the multiplexes where I input the negated bit are all shifted to the back, and all the pairs where I input the bit straight are in the beginning. Okay? Now if you look at this, then you recognize that this is actually kind of a checksum with a very bad performance. So we simply double the message length. And the first optimization, which is also kind of the basic idea of Winternitz, is we append a shorter checksum. So we can append a checksum of length 1 plus log m, which is simply the negation of the sum of ones in the message. And so this sum is represented as log m plus 1 bit message and then negated. And now this checksum has the property that if one bit is flipped from 1 to 0, which would mean someone only has to replace in the signature a secret key element with a public key element, which is easily doable because you know the public key elements. Then a different bit bj will flip from 0 to 1. At least one bit will flip. Okay? So this forces a forger to actually have to invert the one-way function on at least one value to actually forge a signature. Okay, so while this already shortened the one-time signature and also the one-time public key, you can do even better, and that's the real Winternitz idea. So this uses so-called function chains. And a function chain is simply some kind of iteration of a function family. And so the basic chain that was used in the original proposal for Winternitz is given an input x, the ith element of the function chain, everyone awake again, is obtained by applying the hash function I times on the input. So the 0 element in the chain is the identity, so it's x itself. The first element is h of x, then we've got h of x, and so on, until the last node would... can you fix this? The last... Otherwise, I turn them off. The last element in the chain will be... Guys? The last element in the chain will be w minus 1, where w is the length of the chain, w minus 1 times the function applied to the input. Okay? So that's simply a chain of hash values. Now, from this, we can build a signature scheme, and that's what Winternitz proposed. The Winternitz parameter w controls the length of these hash chains. And this also leads to a signature key size versus signature time trade-off. We've got a security parameter n that determines the size of the secret key elements and the output length of the hash function family. And we've got a message length m, which will normally be the length of a message digest. So we will normally first compress the message using some hash function and then sign this message hash. Okay. Now, the key generation first computes some value L, and you will see in the next slide what this L is. And will sample an element from the function family, and then it will sample L n-bit strings uniformly at random. These become the secret key elements. And now, in contrast to these Lampert-Diffie variants, the public keys are not simply the outputs of the hash function applied once, but the output of such function chains of length w applied to these secret key elements. Okay, so we get some kind of graph, so directed acyclic graph, which virtually describes our one-time key pair. Okay, so how do I sign with this? I take a message m, which has m bits, and then first I split this into values in base w representation. So in practice, we currently got an internet draft on this scheme. There we fixed w to be 16. So then this simply means we split m into 4-bit blocks and interpret each 4-bit block as an integer. Then these are base 16 numbers. So the next step is we compute a checksum, which is kind of a generalization of the checksum that I presented before. So it's kind of the negation of the sum of all these entries in some sense. And then we represent this checksum again as base w values. And in total, we will get L of these base w values. So the formula for L is a bit nasty, so I didn't put it on the slides here. You can find this in several papers. It's easy to compute, so normally L will be something like 67, for example, for most of our parameters. Okay, now we've got such an encoded message, and this message encoding everyone can compute. So this is something that also the verifier can later compute because there were no secrets involved so far. And now the signature is simply selecting nodes, one node from each hash chain, and we take the B1th node of the first hash chain down to the BLth node of the else hash chain, and then get the signature which contains L such signature elements, and all these signature elements are one intermediate node from such a hash chain. Okay. If I want to verify such a signature, then I recompute this encoded message. That's something I can do given the message and the parameters. Then given the signature, from knowing these BIs, I know which values in the function chains these signature values actually represent, and simply can finish the computation of the hash chain until I obtain all the end values of the hash chain. If I use this in a Merkel signature scheme, I would use this alternative public key to compute a new root value. If I use it in a standalone version, I simply compare it to the given one-time public key, and if they match, then the signature is valid. Okay, and there are different versions of this Winternitz scheme, and actually the difference between these versions is only in the way this chaining function is constructed. So, as I said, the original paper proposed to simply iterate the hash function on the input. In 2011, we presented a version that changes the security requirements, and for this does, instead of a random walk within the domain of the function, it does a random walk through the function family. So to obtain the ith output of the chain, you take the i-1th output of the chain as new function key and apply this function to some fixed value. And thereby you jump from one function to the next one. And the most recent version is a bit like the first one. The only difference, so we iterate the hash function again. The only difference is that in every round before hashing, we XOR some randomization element, which becomes part of the public key. And this allows us to further reduce the security requirements. So if you look at the security for the original one, we need a hash function family that is collision resistant, undetectable in one way. For this random walk through the function family scheme, we need a pseudo-random function family. And the issue with this one is that the proof is not very tight, so you cannot make very long chains. And for the last one, you need a second pre-image resistant, undetectable one-way function family. So that's more or less like the first one, but we replaced the collision resistance with second pre-image resistance. And the advantage of this one compared to this one, while the properties are like on the same level complexity theoretically, this second scheme has a much tighter security reduction. So you can actually use function chains of arbitrary length. And if you're willing to put some very soft statistical property or requirement on the used hash function family, then you can even get rid of this undetectable in one way. Okay, so that was the latest improvement for one-time signatures. For Merkel signature schemes, the latest scheme is XMSS. And I will only sketch the changes that lead to this scheme. So the overall goal was to get a collision resilience scheme. So we now saw at several points that you actually would need collision resistance if you do the basic Merkel signature scheme. Now, in the tree, we use something similar to this WOTS plus construction. So every time before we hash in the tree, we first XOR some randomization element. And this allows us to prove security again from second pre-image resistance instead of collision resistance. The leaves are normally, so in the basic scheme, they are simply constructed by using a hash function to compress these long one-time public keys. In this case, we use a kind of binary tree with bit masks, again, to compress these one-time public keys. This has the same reason, so the security from second pre-image resistance. As one-time signature scheme, we use WOTS plus, so the one that I just described. For the message compression, we use so-called randomized hashing, which uses an additional nonce for the message hash and thereby gets rid of the security of the collision resistance requirement. And in addition, there's some efficiency or some changes in terms of efficiency. So there's a multi-tree version which means we use multiple layers of trees. The background is key generation can take quite long. So for the key generation, we have to compute the whole tree at once. And yesterday, I wanted to get some recent numbers and try to benchmark for height 20 our own implementation. And after 10 minutes, I didn't want to wait anymore and extrapolated. So this actually, for height 20, this can already be something like 15 minutes. So if you want to do something like height 60, that you get this virtually unlimited number of signatures, then you wait forever. And there's an easy trick to get rid of this. You simply use these many layers of trees. And then in the beginning, you only have to compute the first tree on each layer. So if we take as example this total height 60 and use trees of height 20 on each layer, then we need 3 layers, and we actually just have to compute 3 trees of height 20, which would be something like 45 minutes on a single core, or if you simply do it in parallel, then it can be much faster. And you link these trees by one-time signatures. So you got like the tree on the top layer is used to sign the root nodes of the trees on the next layer, and so on until on the lowest layer the trees are used, or the leaves of the trees are used to actually sign the messages. And then you get, so you can think of this as kind of a certification authority. So then you've got one-time signature for each layer which connects these layers. Okay, I've got half an hour. Oh, and one advantage is actually that you also can reduce the worst case signing time. So that gets a lot cheaper. And so the remaining trees you simply construct one by one while you're signing. Okay. Now, the worst computation part is actually the authentication path computation for these schemes. And this works as follows. So Merkel, in his original paper, which appeared 89, but I think was written in 78 or 79, proposed an algorithm called tree hash. And tree hash takes a tree height and a start index, and then it computes the node on level V, which leftmost descendant is the leaf Li. So for public key generation, you can run tree hash with h and 0, and then it builds you the whole tree. And this algorithm looks as follows. So I've got a graphical representation on the next slide, but just to give you an idea, you've got a stack, and then so if you have a tree of height v, or a node on height v that you want to build, then you have to compute 2 to the v leaves. And so you've got a loop where you always first build a leaf, then you look at the stack. If on the top of the stack there's actually a node on the same level as your just computed node. If it is, you match these two and compute their parent node. Then you look again on the stack if there's another node on the same level, and so on until you don't find a node on the same level. Then you push the computed node onto the stack and compute the next leaf. So graphically, this looks like this. In the beginning, you compute a node, and then you've got this leaf node on the stack. Then you compute a new node. You can already hash because you got a node on the same level. And then you put the parent node on the stack. Next node, you can hash twice, and so on. And the advantage of this algorithm is that it actually needs at most h-1 storage spaces. So it has to store at most h-1 hash values on the stack. So it's much more storage efficient than a trivial way where, for example, you take an array of 2 times 2 to the h, put all the leaf nodes in the right half, and then always hash 2 neighboring nodes into the next 2 to the h over 2 values of the array, and so on. So that's a way how you can build the whole tree, but that eats a lot of storage. Okay, so the costs for this algorithm are 2 to the h leaves plus 2 to the h minus 1 node computations if you use it for key generation. And this is actually optimal, because for key generation you have to touch every leaf and every node at least once. So that's the minimum that you can achieve. For the signatures, if you use this algorithm and compute the authentication path nodes that way, then you have to compute 1 node on each level, which means you have to compute 2 to the h minus 1 leaves and 2 to the h minus 1 minus h nodes. The reason is you actually have to compute the whole tree besides the path from the root to your public key, one-time public key. So this is kind of annoying. It's on the one hand almost as costly as key generation. And you can see that many nodes are computed many times. So if you look over the usage of the key pair, then especially the nodes on the level immediately below the root will be computed 2 to the h minus 1 times each, because the one node is part of the first half of the authentication path, and then the second one is part of the second half of the authentication path. So you're always recomputing these nodes. And okay, so you can do more efficiently if you keep a state, and the currently most advanced algorithm for this is the BDS algorithm by Buchmann, Dahmen, and Schneider from Pico Crypto 2008. And it's an advancement of an algorithm by Pseudo, and I don't remember the co-authors, where they kind of tailored the algorithm for the use in hash-based signatures. Because for hash-based signatures, the difference to general Merkel trees is that the leaf computations are much more expensive than the hash function calls in the tree. Because if you look at this winternets, for example, then you've got L times W hash function calls to compute a one-time public key. And then you have to compress this one-time public key. And that's normally by far more than the hash function calls you do in the tree itself. Okay. So as I said, if you don't have any storage, then you're left with these 2 to the h minus 1 leaf and 2 to the h minus 1 minus h node computations per signature. And okay, so for XMSS with SHA-2 256 and h equals 20, which is kind of a medium-sized key pair, this takes 50 minutes. So 50-minute signature is not what we want. If we store the whole tree, then we have to store 2 to the h times n bits. That's 32 megabytes. Also not really what you want to do. So the idea was to look for a time memory trade-off. And it uses some observations. So first, of course, simply use a state where you store previous authentication paths. Because if you look at how these authentication paths evolve, then you see they mostly change only in a few positions. So every second time they actually only change in one position. Come on, speed up. Okay, and the last one. So if
Hi. I don't expect this to work long. So when you were talking about the height of the trees about 20 minutes ago, I was wondering if it's possible that you could build a Merkel tree of keys that are sort of off path that you could later, by having the root of one key, be used to traverse it as a totally separate thing. In other words, breaking up the keys. And then you could have not a really tall height of that, but rather something that allows you to just have completely separate branches entirely. So you have a key which you're going to use for a day, and then you have like generated a year's worth of keys or something like that. And you can store some offline, which might also be useful, and some in hardware or something. And then you can basically change the way that you use the keys, which also allows you to shrink the size of them.
Sure, I mean, you can do a lot of stuff in this direction. You can do context-sensitive signatures, for example. So you could assign to some indices. These are used to sign documents. These are used to sign emails. These are used to sign, I don't know. So in this direction, there's a lot of possibilities. And then you do not have to store all the keys. I mean, you would have to store some parts of the authentication path, but there are intelligent ways possible to do this. Yeah.
Thanks.
You're welcome. Okay, so continuing with the algorithm. The first observation that we can make is that the same node in the authentication path is recomputed many times. So that's what I said before. If you have a node on level V, this one is recomputed 2 to the V successive times. So for 2 to the V successive signatures. And now I waited too long. Okay. So we can simply keep the authentication path in our state, and then we only have to update the new nodes. And this costs us H nodes of storage, which is not a lot. So that's something like H times 64 or 32 bytes. So that's kind of cheap. And our time on the average goes down to H leaf computations and H node computations. So that's quite nice. The problem is our worst case is still these 2 to the H minus 1 leaf and some node computations. And the reason is when we switch from the left half of the tree to the right half of the tree, we actually got a change in every position of the authentication path. So it's nice to have this on average, but if you have a key pair where some signatures take 15 minutes, some take a millisecond, and then you got again one which takes 7 minutes, that's kind of like a game of luck, and you never know how long it will take, so that's not really nice. So we can further speed this up, or we have to further speed this up. And the second observation is when you got a new left node in the authentication path, or require a new left node for the path, then its child nodes have already been part of previous authentication paths. So if we look at the graphic, then when we switch from the authentication path for this node to the authentication path for this node, then here we've got the switch from right to left, which is always the better switch. And then you've got the left child node of this one is actually still in storage, because that's like the, that was part of the last authentication path. And then we've got one node, so the right child node of this left child node was in storage, or was part of an authentication path 2 to the V minus 1 signatures before. And so by providing storage for these nodes, so right child nodes of left child nodes, we can actually compute every left node with just one hash function call. And it turns out in total we just need to provide storage for h over 2 nodes because that's the maximum number of such nodes that we have to keep in storage. Okay, third observation is that right child nodes on high levels are the most costly. I mean, that's kind of straightforward. The cost to compute such a node is 2 to the height in the tree leaf computations. So the higher, the more leaf computations. And the straightforward idea is to just store the right nodes on the top k levels, where k is some parameter that controls the trade-off between storage and runtime. And then the storage requirements are 2 to the k minus 2 n-bit nodes. And the time that we need on average goes down to h minus k leaf and h minus k node computations. However, in the worst case, it decreased a bit to 2 to the h minus k leaf computations and 2 to the h minus k minus something node computations, but that's still not really great. And that's where the last and main contribution comes in. So that's to distribute the computation. So I already said in the beginning, like for every second signature, we just have to replace one node in the authentication path. So that's really kind of nothing. That's a lot lower than the average runtime. And the idea is to distribute the computations for expensive nodes over many signatures before this node is actually needed. And for this, tree hash is split into two parts. So you've got an initialization, and then you've got an update routine. And this update routine always does one round of the loop. So it's just computing one leaf node and then hashing as long as possible, and then putting the result back on the stack. And that's it for one update. And so for the distribution, you take one tree hash instance per internal tree level, and you start the computation of a new write node on level V whenever the current node on this level becomes part of the authentication path. And then you've got some intelligent scheduling strategy that I will not describe in detail, but this makes sure that the nodes are always finished in time. And then it turns out that it's enough to distribute h minus k over 2 updates per signature among all these running tree hash instances to actually finish all the nodes in time. And so this brings down our worst case runtime from these 2 to the h over k to h minus k over 2 plus 1 leaf computations and some node computations. And the additional storage we need for this is a single stack. So it turns actually out that all these tree hash instances can share the same stack if you do the scheduling right. And this only needs a size of h minus k nodes. And in addition, you need one additional storage space for each tree hash instance, which is separately. So this only costs us 2 times h minus k node storage. And so in total, we get a storage size of this formula and a runtime of h minus k over 2 plus 1. So that's kind of abstract, and in 3 slides I will give you some numbers for this. Okay, any questions so far? Okay, so we currently got an internet draft on this topic. There's a second draft by a different group, but I'm actually not sure if they continue on this. Also because these kind of converged, the 2 drafts. The draft is called Draft IRTF CFRG XMSS hash-based signatures. So if you take this term, search it on the internet, or look at my homepage, you can find the draft. And the difference compared to the scheme that I just described as XMSS is, so perhaps I start down here. So this is actually equal to some scheme which we called XMSST in a recent paper, up to the message digest, which we do a bit differently in the draft. It protects against something called multi-target attacks and achieves tight security. So the multi-target attack issue is in these hash-based signature schemes, you've got many targets, for example, on which you could invert to forge a signature. So there's not just a single target which you have to invert, but there are 2 to the 60 in some cases. Now, if you have 2 to the 60 values for which you can invert to succeed, then the attack complexity suddenly drops by a factor of 2 to the 60, because every time that you evaluate the hash function, even in the generic case, the probability that you hit one of these 2 to the 60 values is 2 to the 60 over 2 to the n, which would be like a direct loss of 60 bits in the security. So that's changed here, and that's why for this scheme you get really with the n-bit hash n-bit of classical security and n over 2-bit of quantum security. We've got small public keys which just have 2n bits. So normally this will be 512 bits for 128-bit quantum and 256-bit classical security. This comes at the cost of the random oracle model for proving this public key compression secure. So that's a bit so the core scheme is still provable secure in the standard model, but there's some annoying dependency between how these public parameters have to be generated and the standard model security proof, and that's why we need a random oracle model to get this proven. All the function families that we use are based on SHA-2. With one exception, we've got some pseudo-random generator in there which is based on SHA-20. And as I said, this is actually, if you look at this scientific work, that's equal to XMSS-T and not to XMSS. And as I promised, some numbers. So thanks to Joost, who actually benchmarked these yesterday evening. So this is a comparison between XMSS as I described it here and XMSS-T. If you look at the signing time, so we've got 2 parameter sets here. The first set is for a total tree height of 20, so you can do 1 million signatures with a key pair. And it's a single tree. And the second parameter set is for a total tree height of 60 with 3 layers. So you've got 3 layers of trees of height 20. Then the signing time for the first parameter set is for XMSS 3 milliseconds, for XMSS-T 9 milliseconds. The reason is that here the hashing is a bit more complex. And actually similar values for a total height of 60. So we've got 3.5 milliseconds and 10.5 milliseconds. The signature size is the same for both schemes. So we've got around 3 kilobyte for the H20 case and a bit more than 8 kilobyte for the H60 case. The public key size, as I said, is 512 bits for these XMSS-T versions, independent of the height. For XMSS, it's 1.3 kilobyte. The reason is that for XMSS, we store all these randomization elements that we XOR in the public key. And here we use the same. We actually use more of these randomization elements, but we let the verifier generate them using a pseudo-random generator. And I don't know why this always goes out. The secret key size, so this contains this, the state for this BDS algorithm. For height 20 is about 2 kilobyte. For height 60 it's almost 15 kilobyte. And the main difference between these two schemes is that for height 20, for XMSS, you get 236 bits classical and 118 bits post-quantum security. And for height 60, you only get 196 classical and actually 98 bits quantum security. And these are because of this multi-target attacks. In contrast, this XMST really gets 256 bits classical and 128 bits quantum security for both of these parameter sets. Okay, so I collected some open research topics as it's a school, so if anyone's interested in working on this stuff, I think one of the main open targets is how to do the message compression in a collision resilient way that provides tight, if possible, standard model security, especially resisting multi-target attacks. This excludes plain randomized randomized hashing. So this RMX stuff actually does not work because then you get a lot of targets still. And this also has applications outside of hash-based signatures. So you've got the same issue for elliptic curve-based signatures if you want to go to the classical stuff, or for letter signatures, MQ signatures, you name it. However, there might be some solutions which actually only work for hash-based signatures where you, for example, reuse the state. The next thing would be the quantum query complexity for further properties. So as I said, for PRF and the undetectability, we so far only conjectured the security level, or took it from some other paper that actually also didn't give a formal proof of this. There are more properties like always sec and everywhere sec and I don't know. So that might be interesting to look at. And finally, one of the things that I find most interesting is actually the quantum security of existing hash function constructions. So in the beginning, I was talking about generic attacks, but who tells us that our hash functions actually achieve also the full generic security when faced by quantum computers? So I'm currently only aware of a single group on the world that works on this in France. And they, for example, looked into how the classical attacks can be improved. So is there a chance to improve differential cryptanalysis using quantum algorithms? Okay. I've got 5 minutes left. That's not enough really to go through Sphinx. I will give you a short primer and then we've got some time for non-existing questions and then we can all have dinner. So the schemes that I described so far are all stateful. This works great for some settings. If you have restricted environments on smart cards, this is actually not a big issue, but in many environments, this is more or less unusable. So if you need to back up your keys for some reason, in my opinion, in most cases, you do not have to do this for signatures, but among others, because of the business model of today's certification authorities, many people want to do this because losing a key means paying for a new certificate. You've got settings like multi-threading, or even when you do load balancing, so SSL termination. Many big companies not do this by one device, but they've got many appliances that terminate the SSL traffic. And some of them actually want to use the same key pair on all their devices. And then you suddenly get an issue because you somehow have to synchronize the states among each other to make sure that you do not reuse the same one-time key pair. Okay, so we decided to eliminate the state. And what came out was Sphinx. And the basic building block of Sphinx is something called a few-time signature scheme. And I will skip this part. The basic idea is a few-time signature scheme is a signature scheme where you can use a key pair for a small number of signatures. And the security slowly decreases with the number of signatures that you make. So for the scheme that we use, you can do something like 8 to 9 signatures with a key pair, then it gets insecure. And okay. So based on this, we developed a stateless signature scheme. And the signature scheme looks as follows. Like with this multi-layered XMSS, actually, you've got kind of a multi-layered XMSS scheme. So that's this top part. And we propose one specific instance with parameters where we choose the height of these trees is 5. And then we use winternets, so WOTS plus, to connect these trees. And on the lowest layer, we use such a few times signature scheme. And the advantage is this allows us for every signature to simply generate a pseudo-random index, and then we use the few times signature scheme at that index to sign a message. And then, like the product of the collision probability of these index selections over time and the success probability of an adversary against forging a few times signature after seeing a certain number of signatures was balanced out such that this is always negligible. And so the whole scheme is designed in a way that all is collision resilient. So we applied actually all these tricks that we used for XMSS. We de-randomized the whole process, so that way we get a deterministic signing. And for a specific instance, which we call Sphinx 256, which gives us 128 bits post-quantum security, we can do hundreds of signatures per second. However, we pay for the statelessness with the signature size, which is 41 kilobytes. That's not terrible, but also not nice. And our keys are 1 kilobyte keys. However, that's the first proposal, and actually I think there's a lot of work that could be done to further improve this. And especially one open topic in this direction would be to develop more efficient few times signature schemes, because the few times signatures really eat up most of the efficiency. That's it from my side.
Questions?
You mentioned there is a group in France who is doing research into post-quantum security of existing hash functions. Can you give a few names or
Mark Kaplan. Yeah. I think they are at INRIA, but yeah. The question was about this group in France which does security analysis of existing hash functions under quantum attacks. And that's Mark Kaplan's group, and I do not remember the remaining group members, so yeah. Okay, then I guess.
My question.
Ah,
No, for Sphinx, how many signatures you can tolerate?
So-
the parameters acceptable.
so the parameters that we gave are computed with assuming 2 to the 50 signature queries. You can do more, but then security slowly drops. So like for every signature scheme.
It's the end of the day. Thank the speaker.